Have a good posture, breathe, smile, talk clearly. Do not read your notes out loud. Oh, wait. So that was a joke. Jesus. Come on. Oh, my God. It's the worst crowd. So actually, I downloaded the conference app, and there were some people signed up for my talk that are not here. So are they lying on the internet? I don't think that's ever been done, right? So who used a software library? Show of hands. Good. Who wrote software library? Good. Same people. I think you're just the ones that want to raise hands, but who knew that today was National Puppy Day? Oh, fuck. Sorry. I forgot one joke. So I just want to say I'm really passionate about writing software libraries. So this should be like the side note of the title, how to design software libraries otherwise. So who knew that today was National Puppy Day? Nobody. Today is National Puppy Day. Just nationalpuppyday.com. So who am I to talk about software libraries? Turns out I'm the author of several software libraries in Elixir, which sounds really dumb for me to say, because for years I thought that several meant like a shit ton of stuff. But it turns out that several means like more than two, but not many. That's the definition of several, which is true. Like I authored more than two, but not many libraries. But it's so silly for me to say. But I really love working on libraries. It's how I got started with Elixir and learning Elixir. I really love to improve the ecosystem, to give back to the community, and to write stuff that I end up using anyway. So, and I really want to talk about mainly two things. The first one is the what of software libraries. So what are they? Why do we write them? What do we do with them? And the second one is the how of software libraries. So how do you write, design, think about a software library, and evaluate if a software library is good or bad. And my point is that writing good libraries, I think, is quite hard, and especially if you don't have either experience writing them, or you don't have guidelines on writing them, and you don't think about this stuff. So my name is Andrea, and I'm the one on the left in the picture. That's my handle on GitHub. I work at a company called Forza Football, which we make a football app with live scores and football data, soccer for US people. But I don't really care about football at all, but that's okay because the company is just a facade for harvesting core team members of Elixir. So this is the whole Elixir core team, and these are the people that work at Football Addicts. So we're just trying to like gather all the core team members that we can. We still don't know what we're going to do with them, but yeah, we're harvesting them in the meantime. And you may have seen that my face is up there, so I'm in the Elixir core team. And yes, they know. So I come from Italy, from a town that's called L'Aquila, which should be fun for you because it literally means the eagle. I think US people have a thing with eagles, right? Yeah, and it's a pretty small town, but we do something really famous, which is saffron. So like the proper Italian saffron comes from where I'm from. And this is why I like to call L'Aquila the San Francisco of Italy, or just the San Francisco, right? I'm on a roll. So this thing is Sweden. This is a map I drew of Sweden, and I actually live here in Gothenburg, Sweden, not in Italy. Even if I'm taking some time off traveling right now and doing the digital nomad thing, which has been really hard because I've traveled really not a lot of time compared to the time I spent in Italy. Because, I mean, Italy, just the food and the sun is so hard to live. Okay, so just want to get to the meat of the talk, or tofu of the talk if there are vegetarian people around. Thanks, the guy laughing is just like melting my heart, thanks. So the first thing is, what are software libraries? Why do we write them? Why do we use them? And I think the key word is abstraction, right? So we tend to write software libraries to abstract stuff. And we tend to use software libraries because we want to use those abstractions. So we write libraries when we want to abstract stuff that is general enough to be reused in multiple things, but they don't fit really in the programming language or ecosystem where the library is, which library lives, basically. And from my experience, I think we mainly abstract two things, two types of libraries. So we abstract mainly two things. And the first one is we abstract complex code, right? So we abstract code that is easy to get wrong, that is full of corner cases, that is not application specific. So just complex code that we don't want to write over and over again, and we don't want to get right over and over again. And the other thing that we tend to abstract, I think, is patterns and ideas. So when we abstract patterns and ideas, we abstract things that give you tools to shape solutions for problems. So shape the solutions to your problems instead of just drilling down and abstracting just complex code. So they kind of give more context to solving problems. And I think these two types of abstraction, so complex code and patterns and ideas, map to two main types of libraries, which I came up with because I couldn't find any literature on this, so this may be bullshitty, but I think this, from my experience, it boils down to two types of libraries. And the first one I called, let me handle this for you. So I will find better names, but let's go with this for now. But these kinds of library are basically the ones that abstract complex code. So they're libraries that just take away the complexity from your library, but keeping a very simple surface from the library, basically. So I think an example can make this simpler, and a good example is database drivers. So database drivers, what they do is they abstract away all the complex parts of communicating with the database, right? So the network interactions, the protocol, the mapping of data with the database. But usually the API of a database driver is quite simple in that it just maps what you can do with the database and it ports it basically to your programming language. And in this, they just abstract all the complex interactions with the database, but they don't do much more. They don't introduce weird concepts. They just map basically the database to your programming language, right? So let me handle this for you means that you usually just give them something to do, and they do it, and they return something back. And a good example of this, another good example is calculation library. So if you have a library, for example, to do integrals or whatever, the code tends to be kind of complex, and you don't want to write over and over again. But it's really like the surface of the library is really simple. So you just say integrate this function, spits back a number. It doesn't introduce weird concepts or new ideas, basically. And a concrete example of a library that falls into this category that I wrote is Redis, which is a Redis client for Elixir, a Redis driver. And so the surface of this driver is really, really simple. So it's just, you can spawn a new connection, which just instantiates TCP connection with Redis. And then you can issue commands to Redis. And as you can see, it maps kind of maps one-to-one to what you can do in Redis. Just open a Redis console and send commands and get responses back, basically. But the code that lives in the library is more complex than that. It handles stuff like the TCP connection, the network stuff, the network going down and reconnections, and it handles the protocol for Redis, and handles multiple clients wanting to connect to Redis concurrently. So the code is more complex, but the surface is really what you would expect from just a very dumb, simple driver, right? So this first category of libraries, they abstract complex code, basically, without introducing too many new concepts. But the other category of libraries, I think, the other extreme, basically, is here's how you handle these libraries. So these are libraries that kind of try to shape the way you think about problems and the way you solve problems. And a good example of this is right in Erlang. I think it's behaviors. So behaviors tend to abstract. They're not properly libraries, but they do abstract some patterns, right? So for example, in Erlang, it's really common to have a process that keeps some state and that serves requests and response, so like a generic server, basically. And we have gen server for that. And that abstracts away some complex code as well for dealing with system messages and all this stuff. But it also gives you terms to talk about and think about your problem, basically. So when we say in the Erlang community, when we say Gen server, we know what we're talking about. So we have this abstraction that we can talk about. Another example of this kind of libraries are frameworks. So frameworks usually tend to fall into this category, in my opinion. So take a thing like Rails or Django or Phoenix. The code is not super complex, especially Phoenix, but the behavior, basically the concepts that they introduce to solve the problem of web frameworks or web requests they provide a lot of tools to do that. An concrete example of a library that I wrote that falls into this category, in my opinion, is a validation library that I recently released called Soul. So this library is for validation and conformation of data, which is a quite common problem. So validating possibly external data and conforming it to a given schema. And the validation itself, it's really application specific. You can't really abstract away how you validate the data, right? But you can abstract away the tools that you use to validate the data, to conform the data, and the tools that you use to talk about validating data. So the real value I think that this library provides is basically just ideas. So it introduces the idea of a validator, which is something that takes a value and says if it's valid and it conforms it, or it just says it's invalid for a given error. And then it provides ways to combine this validator. So like this one-off would combine a bunch of validators, and then the first one that succeeds, the whole validation succeeds. So it provides just the idea of validators and the ways to combine these validators, but then you have to write your own validators. In this case, we use like some boolean functions, but in your application, you're probably going to write your validators for your application logic. So it's kind of and the code for this library is super simple. So I think the real value is just but the API, for example, is not that small because there's a lot of like combinators for validators. So and it provides, the value that it provides, I think, is just the ideas, mostly the ideas at least, not really the complexity of the code. So these two kinds of libraries, there's not a hard line between them. I think that many times they overlap, the two categories overlap. And many times, here's how you handle this category kind of includes the let me handle this for you category, because there's a lot of very big libraries that introduce a lot of ideas, but have a lot of complex code in them to support those ideas as well. So this is I think what are software libraries, why we write them. So the keyword is to abstract, I guess. And the next thing that I want to talk about is how the meat. So how do we write software libraries and think about software libraries? And I want to do this in terms of what makes a software library good. Because if you know what makes a software library good, in my opinion, of course, and if you know what makes a software library good, you're going to be able to think about this stuff when you're writing a software library. You're going to be able to evaluate software libraries when you have to use one. So if you have this set of criteria to strive for or evaluate libraries. And the first criteria that I would say is that a software library, I think, should be extensible. So extensibility is a really important quality. And if you don't have extensibility, basically your library is locked in and can only cover a set of use cases that users are going to have. And either they can cover all of them by loading the library, or they can cover only a part of them and let users with nothing to use when they need cases that you don't support, right? And I think extensibility is all just that. So basically, you support all the use cases that you can, and then that it makes sense in your library, but you provide extensibility points for when users need to do something that is outside of basically the common area. So they need to do something specific to their use case. They can just extend your library to do it instead of just dropping the library. And I think a good rule is like 80-20 rule about having 80% of your library of the common use cases covered in your library, so built in your library, and 20%, the remaining 20% be extensible. So if you have, what this means like the 80% of the most common use cases should be implemented in your library so that you actually can, as a user, you can just write a small amount of code to achieve what you want to do in these common cases, right? But the remaining 20% is for when users have a more particular use case, so then they just need to write a bit more code, but they can still take advantage of your library, basically, instead of having to drop it. And a good concrete example of this that we have in Elixir is in Elixir's build tool, Mix, which is kind of similar to Rebar. So Mix provides this mixed shell behavior, which is a way to basically write backends for the mixed shell. So when you output info messages or error messages when running mixed commands, you can have them go through a custom behavior, custom mixed shell, basically. And this is configurable at runtime, and it's swappable. And having this as a behavior, it's already the 20% extensibility part, right? Because having the 20%, having the mixed shell configurable means that if you have a weird use case where you have, I don't know, you need to send messages to a file or to Slack or whatever, then you can write your own backend basically for the shell, and it's going to be enough. But since there are more common use cases, there are some very common use cases, we provide some of those as well. So basically, you can say, if you want, we provide mixed shell I/O that just prints commands to the standard output. We provide mixed shell process, which just sends messages to the current process so that you can use that in tests to assert that something was printed on the shell. And mixed shell quiet just mutes all messages. So these are quite common use cases that you would end up probably, not all of them, but you would end up implementing some of them in your application. So it makes sense to provide them so that users don't have to write them. But they're still just part of the whole extensibility mechanism. So they're the most common use case that are already covered. And just you write this line of code that says switch to mixed shell I/O, and you're fine. And you don't have to write any other code. But if you have a weird use case, you can just hook into that, basically. And a good thing about extensibility, I think, is to have get out of jail points in your library. So I read this get out of jail points in a library, and it's stuck in my head, because this is like, if you have a library, it's going to probably abstract something, as we said. And when you abstract something, you're going to, so I read about this article that theorized this law of leaky abstractions, which says something like, if an abstraction is complex enough, it's going to leak. And leak meaning that it's going to make, it's not going to map one-to-one to the thing that it's abstracting on. You're going to lose some features of the thing that you're abstracting on in order to abstract a level above, right? And if you have these get out of jail points, you can try to basically fill the holes in the abstraction, because you can let users drop down to the lower level of the abstraction so that they can do stuff at the lower level, so they can just talk directly to the thing that the library is abstracting, basically, instead of going through the library. And a good concrete example is, I think, the fragment function that we have in Ecto. So Ecto is a database layer, basically, for Elixir that supports multiple databases, and it has a quite rich query language built in Elixir. And this query language provides all sort of SQL functions, basically, like where, select. So it makes it easy to build queries out of Elixir, but it can cover all the functions that you can come up with when dealing with SQL queries, right? Especially because since it supports multiple databases, there will be databases that don't support given functions. So it will be hard to get a one-size-fits-all query language. So if you have, with these fragment functions, basically you can pass any string and integrate any string in an SQL query, and you're still going to get, this query is going to still be sanitized. It's going to still get some compile time features out of the query language, but you can drop down basically to the lower level of abstraction. So the abstraction layer is over the query, the SQL query language, basically. But you can drop down to the direct SQL language and just put a piece of SQL in your queries, so that that abstraction doesn't leak anymore. You have a way to stop the leak in the abstraction. So a good software library definitely has to be extensible, in my opinion. And another super important characteristic, I think, is composability, right? So good software library has to be composable. Composable? maybe. Mostly composable, I would say. Composable. All right. What? Okay. Yeah, not really funny. So composability, I think it's really important when trying to write a software library and when using a software library. So by making a library composable, basically you're allowing it to be plugged into existing systems and to be used together with other components of the system that are composable as well in the same way, right? And to achieve composability in a library, so one of the things that I try to strive for is to use the existing language features in the language you're writing the library in. So if you're going to use existing language features, probably there are other pieces of software in that language that are using the same language features, and probably the language provide tools to use these features. And so you're going to make your library composable with the existing ecosystem, basically, by using the same language features, right? An example of this in Elixir is stream. So Elixir provides this notion of stream, this abstraction, which is an abstraction over lazily computed collections. So collections where you can compute the next element just on demand when you need it, not eagerly. And so this is part of Elixir, it's part of the language. And so me and a friend of mine wrote a Cassandra driver in Elixir. And basically, Cassandra provides a way to paginate queries. So you can get just a subset of the results of the query, and then you issue the query again with a different offset to get the next subset of the query. So you don't have to load the whole result set from the database when you want to do a query with a large result set, for example. And basically, if you think about this set of pages that form the result set of a query, you can think about it as a stream, right? Because it's a collection of pages, and you can compute the next one on demand by just issuing the query again and getting the results. And so basically, we provide this function called Cassandra stream pages, where you provide a query, and it returns a stream of results for this query. And since this returns a stream, and a stream is something that exists in Elixir, we can use Elixir tools to work with it. And one of the tools that we can use, that I really like, is this task sync stream function. So this function takes a stream, and it basically is a parallel map. So it maps a mapper function over the elements of the input stream, basically, and in parallel. So it spawns a process for each element of the stream. It runs the function, the mapper function in the process, and then it aggregates the results and returns another stream. So it just basically processes the stream in parallel and returns another stream. And with a bounded set of processes, you use a bounded set of processes, basically. You don't spawn one element for one process for each element in the stream, but you have like a window of processes that you can spawn, and you process windows of elements in the stream, basically. And this, if you provide a stream, if we return a stream from Cassandra stream pages, we can use this function to basically map over, in parallel, over pages of results that we get back from Cassandra, right? So you get back, each page is going to be processed in parallel, and the result is going to be returned in a further stream, basically. And then we can use something like enumReduce to aggregate all the results of the mapping in a single final result. And if you take this example, so there's 3 lines of code and only one we actually implemented, right? The other one are just, they're just available because we chose the right abstraction and the right existing language feature. So by returning a stream, which is, and again, an existing Elixir concept, we can use all the tools that Elixir provides to work with streams. So we're going to get like a lot out of just language and the libraries that the community could have built that work with stream, but just returning a stream, basically. So using language feeders definitely helps with composability. Another thing is to, I think it helps if you know the existing conventions. So if you know the existing conventions in the language and in the ecosystem, you're going to be able to to compose your library with the libraries and tools and code in the ecosystem that uses the same conventions, basically. So a convention in the Erlang world is to return from a function that can fail is to return OK term if the function is successful and return something, or error reason if the function is not successful and errors out with a given reason. And in the Solve, the data validation library that I mentioned earlier, I basically started out with validators being just functions that return this, right? Because this is, so if the validation is successful, they return OK and the conformed term, which can be the same term. Or if validation is not successful, if the term is invalid, they return error and a reason. And by doing this, I was able to start out with something that already exists basically in the Erlang community. So there's a lot of functions already that have this signature, right? That have OK term when something goes right and error term if something goes wrong. But then to make the library even more composable, so I thought that predicate functions that take arguments already are some kind of validation in itself, right? So, for example, guards, like is binary, is process. They're validating that the thing that you're giving them is what, like, is a binary or is a process. So I thought that it would make sense to have validators be also functions. They can be also functions that return a boolean instead of OK term or error term. And this would just mean true if the data is valid and there's no need to conform it, and false if the data is not valid. And by doing this, I was able to use a much wider range of functions that already exist as validators in Solve, basically. So I made this, so you don't have to write wrappers around Boolean functions in order to convert them into validators. Basically, that's the idea. So the library became more composable by choosing the right convention, basically. So library has to be extensible, as I said, has to be composable, and I would say that has to be easy to use in order to be a good library. So when you're when you're writing a library, try to strive for easiness of use. And when you're seeing a library that is not easy to use, there's usually something fishy going on. But to be easy to use, I think, so a library, I think a good quality is to be easy to use are consistency. So consistency, I mean consistency in the API of the library, consistency in the ideas behind the library. And I think this is summed up, I think, by something called the principle of least astonishment, which kind of means don't break the expectations of the user. So don't do something that would surprise the user in your library. So just be consistent, be coherent in your library. Another good quality to make a library easy to use, I think, it's transparency. So I usually try to write libraries that provide an abstraction that is thin enough that you can kind of see through the abstraction, right? So if you write a library that has a huge abstraction layer, basically that abstracts so much, it's really hard to get what's going on when you use the library, right? But I think if you write more libraries that are thinner and that have like thinner layers of abstraction and you compose them, it's going to be easier to both drop down to the lower level of abstraction, also to understand what's going on in general. And one concrete example I think I have for this is to be transparent in the resources that your library uses. So for example, Redux, the Redux client I was talking about earlier, is pretty transparent in the resources that it uses, because it says if you spawn a process, a Redux connection, basically, I'm going to use a TCP connection to connect to Redux, and that's all the resources I'm going to use. And by doing that, I basically give control to what resources are in use to the user of the library. So the user can decide if I want 100 TCP connections, I just have to spawn 100 Redux processes, right? So I don't hide anything about the resource usage, and I give control to the user, and this makes, I think, the library more transparent, because then the user can basically decide what to do based on their needs. And the last thing to be easy to use, I think a library has to have super great errors. So never do something like this, because never basically ignore the expected failing case, right? So if there's something that can fail in a library, usually try to address it. Libraries are generally not the best place to have let it crash in practice, basically. Because you really you don't want people to have to dig in the code of your library to find out what's wrong, find out where the error was. So I usually try to strive to provide good error messages and possibly even solutions, suggestions on how to solve those error messages, solve the problem that caused error messages. And actually, the last thing that I think it's important to have a library easy to use is documentation. And actually, let me blow this up. It's really, I mean, this is really super important, I think. And I never write anything without, I try never to write anything, even internal code, at work without writing documentation for it. Because when I write something, I'm the writer, I'm the author of that. But like 6 months later, I'm usually a user of that. I'm not touching that anymore. So it doesn't make sense that I have to read the source code to find out what's going on with my library just because I wrote it. Since I'm acting as a user of it, I should just be able to look at the documentation as any other user of the library. So I try to write documentation just for myself, basically. But I think library without documentation is just, usually, I just tend to drop it and not use it at all, because it's just too hard, I think. Documentation is another level, basically, of, it's different than having to read the code. So documentation is for humans, code is for computers mostly, right? So library, as I said, has to be extensible, composable, and I think another easy to use, and I think another good quality is focused. So this is something that plays well with composability, I think. So a library that is focused, that doesn't try to do too many things, is going to make writing the library and using library much easier. Because if you strive for composability as well along focus, basically you're going to have a kind of small focused library that does one thing, but it's easy to compose with other libraries, and then you can make the system as complex as you want. But the pieces remain as simple as possible, or as focused as possible, and they basically try to do each does one thing and it does it right. So we talked about what are software libraries, why do we write them, why do we use them, and the keyword is abstract, as I said. So we write them to abstract complex code and to abstract patterns and ideas. So we have on one side this let me handle this for you libraries, as I call them, that abstract complex code, and on the other side we have here's how you handle this library, I call them. So libraries that abstract provide mostly ideas and patterns instead of code. And then we talked about how to write a good software library, what are the criteria, what are the qualities that make a library good. And I mentioned extensibility, I mentioned composability, easiness of use, and focus of the library. And I hope that I've given you some criteria and tools to evaluate libraries and to think about when writing libraries, so that we can all improve the ecosystem together as users and writers of libraries. Thanks. We have plenty of time for questions, right?
Yeah, definitely. Yeah. So bring it on for questions. Yeah, all right, I'll just read on there. You haven't mentioned unit tests. Like,
unit tests. I mean, should I even mention that? Of course, just write unit tests for all the code that you write. That doesn't. I didn't even mention like write comments or write indent code correctly. I mean, yeah. Yes, do all the stuff. When you write a library, do all the stuff that you do for all code that should be done for all code in the world, and also do this stuff. That was the point.
What about performance, right? And how do you like trade that off, right? If you like want to wrap something, and kind of give the user the same amount of control, right? Kind of. I can have better performance, or I can have worse performance, and I can make this trade-off versus like the library makes this trade-off.
Yeah. So I think one thing is that this is a really good question, and I think one thing is that if you can't focus only on performance when you're writing a library, I think, because it's gonna compromise all the other things that the library is trying to do, all the abstraction. And I think if you need performance really bad, you're probably not going to you're probably going to roll your own solution anyways, if it's so critical to you. So I usually try not to strive, it's kind of 80-20 again. I mean, I try to do like 80% that I try not to slow down things too much, but I don't destroy the library just to make it super performant, but unusable or hard to use or hard to understand. Because if you need that user performance, first of all, maybe you're not using the right tools, maybe you're not using the right abstractions, but maybe you want to roll your own solution anyway. So I try not to strive too much for performance. I just try to, I think, was it Joe Armstrong that said write it should work, should be pretty, should be fast in this order, I think. So, yeah. Sorry?
Wait 10 years if you want to be fast.
Yeah, that doesn't work anymore, but yeah, that was the line.
Yeah.
What do you think of code that injects, like a lot that injects code, for example, plug?
Code that injects code in your stuff. I usually don't like that. I think that kind of goes against the transparency of things, right? So, I mean, so plug is kind of an exception because I think plug, since it's a very famous library, right? And it's very much in the, I think, in the here's how you handle this category. So it's kind of a library that introduces mostly ideas, right? It does code as well, but it's introducing a lot of concepts, so we talk about plugs like we know what they are, right? But they're not the thing outside of plug, right? So it's introducing this concept. And these libraries, and especially libraries that are like institutional, for example, plug is an institution for Elixir, right? Is how you do HTTP in Elixir, arguably. And so they're more, I think, they're kind of allowed to do this because they're super documented. Their users use them a lot, so you really know what's going on underneath. To some degree. Sorry? Yeah. Yes. So, and basically, yeah, I think that so this kind of libraries, they're kind of more allowed to do it. They're kind of forgivable when they do it because they're so famous and people have so much terms to talk about them basically. But in general, I try not to do that at all because it's just it's an abstraction that it's really hard to, like, injecting code is something that is really hard to make transparent, right? Because how do you show the code that you injected? So it's hard to document. So it's kind of, I try to stay away from it. But when I do, so a good example in plug, for example, is or in general, it's when you define functions in a module, through use, for example, in Elixir, right? You inject functions in a module, you define functions in a module, basically. In that case, I always try to define a behavior for those functions. And when I inject the function, I inject the at behavior line as well, and then I document the behavior, basically. So I say, like, these are the functions that are generated, and I document them as callbacks of this behavior, basically. This is one thing practical thing that you can do. I mean, and I think that plug probably does this, at least for plugs. I mean, when you create like plug router, it defines call and init for you, and they're documented in the plug behavior. Yeah.
Any more? No? All right, then, thank you.
Thanks.